To graph absolute value functions, again, we want to be able to find the zero of this inside function. Okay, to find the zero of the inside function, we want to find that because that represents the boundary between the positive and negative versions of the inside. So where the absolute value will not affect the expression and when the absolute value will flip the expression. So the zero of this function is going to be, the inside is going to be at x equals positive 3 over 2. So that's going to be the boundary. So at positive 3 over 2, in fact, I'm going to put positive 3 over 2 here, and our y value is going to be 0. So that's going to be the boundary point. So we have the positive versions and negative versions. So when I plug in 2, the x value, the y value is going to be 2 times 2 minus 3, which is 1. Okay, plug in 4, 2 times 4 minus 3 is equal to 5. And we have the domain of the positive function, so the positive version of this as a piecewise function. The domain will be from the boundary to the right. And we can express this as y equals 2x minus 3. Okay, so that would be the positive version of the function. So then we have the negative side. So when we plug in 0, we're going to get negative 3. Absolute value is positive 3. Negative 2, we're going to get negative 7. Absolute value is going to be positive 7. So for the negative side, the domain is going to be x is less than 3 over 2. Okay, so then we can describe this as the negative side. So since it's negative, the expression 2x minus 3, because that expression is going to be negative, we need to convert it to a positive by making it the opposite. So then we rearrange it to negative 2x plus 3. Okay, so there's our graph. Those are the piecewise function. I'm going to graph the coordinates here. So at x equals 1.5, we're going to have it equal to 0. At x is 0, positive 3, negative 2, positive 7 up here. Okay, so this represents the negative version of the graph, and it stops here, but that function does continue, but for our purposes, because it has a domain restriction, it has to stop at that point. When I graph these coordinates, 2 over 1 up, 4 over 5 up. Okay, so these are not symmetrical points, so that's not, we want to try to get symmetrical points, but there's our graph, and then because the domain stops there, we have our graph that looks like that. Okay, so the solid lines represent the function that we want. Okay, the dotted lines represent where that graph would continue beyond its domain. Okay, so when we look at the graph of absolute value of x squared minus 2x minus 8, we really again want to know where the domain of this starts. Okay, so we need to know where the 0 is of the inside. So we're going to factor this. So we're going to do minus 4 plus 2, and then we know our 0 points are going to be at 4 and negative 2. So I'm just going to put those into our table of values. Okay, and that represents the 0 points of the graph. So that's our domain boundaries. So we know that part of it is going to be above and part of it's going to be below. We can just test this if we like. So if I kind of have an idea what part's going to be below, because we know that this is a parabola facing up, so we know that in between the zeros we should have below the x-axis. Okay? So I'm going to choose the vertex point, which is going to be halfway between these 2 points at positive 1. When I plug in positive 1, I get negative 3 times positive 3. That's going to give negative 9, and then absolute value is positive 9. And then we're going to have the positive domain. It should be on the outside of that parabola. So we're going to choose maybe negative 3. Plug it in. We're going to have negative 7 times negative 1 is positive is negative 7. Absolute value gives us positive 1. Actually, sorry, that's going to be negative 7 times negative 1, which is positive 7. For 5, we do the same thing. It's going to end up being positive 1 times positive 7, which is 7. Okay, so the black represents our domain boundaries, the green represents our positive version, the red represents our negative version, so we can write this as a piecewise function. Okay, let's draw this graph first. So I'm going to first of all identify my 0 points. So negative 2 and 0, 4 over 0. The parabola where it was flipped, it's going to be at in between, so it's going to have our vertex like this. Actually, this is going to be the solid part. This is going to be part of the function. And the domain restriction is only for in between, so these dotted lines represent the part of the graph that doesn't exist. Okay, and so then the other portion of the graph is going to be where it's going to be above the x-axis, and this is our parabola that's going to look like this. Okay, and it will have our mirror image here, so that is the domain that doesn't exist here. Okay, so those two parabolas, one's upside down, one's right side up, make up the absolute value function. So we should write this as a piecewise. So my positive function, the domain is going to be on the outside. So when x is less than or equal to negative 2, or when it is greater than or equal to 4, it's going to be just the positive version of that parabola. Okay, and then the negative version of that parabola, okay, where we would end up flipping it, the domain is going to be in between negative 2 and positive 4, and then the function is going to be y equals negative x squared minus 2x minus 8, or if I rearrange it, it's an upside down parabola with negative x squared. Okay, so there's our piecewise function if we were to write this as a piecewise function.